Welcome to Reality Creative Video. I'm Hermes, and I know you guys love my updates, especially when they're involving platinum and high voltage AC and stuff like that. So I got updates. I've been working on stuff. So remember that batch of platinum I made? It took a week to cook. I got it to 10 parts per million. The taste on it was horrific. What a strong tasting solution. I mean, it made copper, strong tasting copper, seem mild. So I didn't know exactly what was going on with the taste in that solution, so I threw it away. I know, 10 parts per million, but I wasn't sure if it was because of a whole week's worth of material that I kept dumping in there. I was trying different things out, and when it comes to materials that you cook, if you're skeptical about a particular material for one reason or another, always err on the side of caution and throw the material away, even though you might be throwing away good parts per million or something usable, or maybe you can use it as a topical, for topical. I tossed it out because I got tons of topical platinum sitting here, so I don't need any more. So that led me to a search on where this taste is coming from. Now, normally I cook platinum to what I've been cooking platinum to is from being 1 and 3 parts per million, maybe 4 parts per million, and it does have this kind of taste to it. So I had to hunt down where this taste was coming from. So I put all the chemicals in to a beaker here, one at a time, and then I did it one at a time, and then I put them, finally got it all in there once, all the chemicals in here that I use on platinum, and I heated it to 80 degrees C for 3 hours, and I just let it cook in there. And I did not put any platinum in there, didn't do any electrolysis. And after 3 hours, I tasted the solution, and the solution was good. Tasted like a little bit of a vanilla on it, and that's normally, without the little bit of platinum taste in there. So that told me that at least the chemicals were not adding to the taste problem. So then I proceeded to put the platinum rods in there. Now, there's another part of this procedure. The taste thing had gotten me looking online of what other people are selling. So other manufacturers, which they don't disclose how they're making their material, their platinum, say that it is colorless and tasteless. Well, I'm questioning the tasteless part. The colorless part, as you know, the reason we have color in the platinum is because of the caramelizing actually winds up being because of the caramelizing of the honey. I thought it was the caramelizing of the ascorbic acid, but it's not. It's actually the caramelizing of the honey. So another thing that I, branch off I'm working on here is creating colloidal platinum clear. And that's what I got here in this brew bottle. I'm experimenting with brew bottles, as you know, for now, at least on platinum on gold, and platinum gold anyway. So anyway, this is what I call platinum clear. It's absolutely clear platinum. It actually has a shine to it, as if the silver or the platinum molecules are reflecting additional light out of it. And according to online, that's what their platinums look like. They don't show a picture of the platinums. That's how they describe it. So I managed to cook this platinum clear, which I'm going to share on a start to finish because I think it's absolutely exceptional. It does not use, it's basically the same thing as the start to finish that I did with Manuka honey, but no Manuka honey at all. What I use instead is 10 milliliters of ascorbic acid. I still do everything else that's in that video. And I cook it to no more than 80 degrees C. I do not let the temperature go over 80 degrees C, which means I have to limit the current a little bit more down to about under 1,000 milliamps. But anyway, I will have a full show on how to do it. And that cooks this. And in 3 hours, you'll have about a 2 parts per million platinum solution, which is pretty darn good compared to what we had before. So, and the 2 parts per million solution has a reasonable amount of taste. It tastes what the other platinum that I had cooked before tasted like. Not like the 10 parts per billion platinum, which was really strong. So anyway, this got me into the wondering where the taste was coming from. And I believe the taste is coming from the platinum dioxide. Now, when we cook copper, if I don't cook it properly, what I get created is excessive amount of copper dioxide. And that is what it contributes to the strong taste in copper. Now, the new process that I use on copper is much better, and the taste on copper is very, very mild now because I've limited the copper dioxide that gets created. So, I need to do the same thing with platinum. When we cook it with low voltage electrolysis, we need to eliminate the platinum dioxide. At least that's my theory. So, to support that theory, over here in the high voltage AC lab, I have a batch of colloidal platinum cooking, so far 9 hours, with just distilled water in it. Nothing else. It's got no sodium, no washing soda in it, no flavoring, no nothing. It's just distilled water, which is what these other manufacturers advertise, on that their product has. Now, it's an extremely slow process. I cooked this so far for 9 hours, and I got 200 micrograms of material off. That's not a lot of material. That means in order to get 2 parts per million, I'm going to have to cook it for a long time. But my idea with it is at least I want to get it to about 1 parts per million to compare taste. I want to see if cooking it with I don't believe we're getting any platinum dioxide in the high voltage AC process. At least I don't believe we are. So I want to compare to see if it's the platinum dioxide that's causing the taste in the platinum. Just for my own stuff to know. So that's what's going on there. Now that has evolved into a couple other things that I've discovered with high voltage AC and platinum in general as far as cooking platinum is concerned. I find that the closer you can put the rods together, the more efficient and the faster you can get material into the solution. Now that is very different from like when we cook silver, we have to have the rods as far apart as possible so to minimize the amount of silver that is going to get stuck to the opposite rod. Now with platinum, we're looking at a substance that's different, extremely hard, and with the stirrer cranked up at a really high momentum, there isn't too much of a problem. And with using 2 platinum rods, if the platinum gets stuck to the other rod, well, next time I cook platinum, I just swap the rods around, and then that platinum comes off and is reused. So it's not a big deal if any of the platinum gets stuck from one rod to the other, but the closeness of it reduces the energy necessary to burn the platinum off the material. So what I want to do is I want to increase the speed that my high voltage AC process is going on. And to do that, I need to bring the platinum rods closer together. I did short-term experiments on it, and I had good results with that. But I need a new top. So I have to print a new beaker top, which is printing over there right now. It's a low mass beaker top because I didn't want to wait 6 hours for the thing to print up. So this one will print up in 3 hours. It has the 2 leads closer together. We'll show you a picture of that. And I'm hoping that that's going to cook the platinum much faster. Not only using high voltage AC, but also with the low voltage DC process as well. I also find that having the rods closer together with platinum gets the stuff in there quicker. Now, all these little advances that I've come along have helped a whole lot with the new method of doing platinum, which I'm calling platinum clear. This platinum clear cooked in 3 hours to 2 parts per million and has a decent taste to it. A little slight vanilla taste because we've used the vanilla flavoring. I think the glycol and the vanilla flavoring actually helps the process of creating, of help burning the platinum off. Though I can't prove it 100%. I've seen it with other experiments. It's hinting that the glycol in the vanilla flavoring helps. So if you're not using flavoring with glycol in it, you may not get 2 parts per million in 3 hours like I'm getting. It might take a little bit longer, but that's a hell of a lot better than the 6 to 12 hours that we had at the original start to finish, just using the Manuka honey. So, the no Manuka honey and just 10 milliliters of ascorbic acid. But I will have an official start to finish on this method in a week or two, as soon as I hammer out the fine details, like what top I'm going to be using and stuff like that. So that brings me to parts per million, my discussion on parts per million, and why we're talking about this. Parts per million, this is the general formula for parts per million. Now, that's just a general formula. Now, when you go online and you look at colloidals, look for colloidals, they tell you how many parts per million it is. But really, you have no idea if that parts per million, what that parts per million means, because they don't tell you how they measure their parts per million. Now, how I'm learning how to measure parts per million, I like to know the amount of material that's coming off. That's important to me, especially when we're cooking platinum. We need to know the amount of material. But determining parts per million is something you need to do with a microscope. Either an electron microscope or my laser microscope. The guys in the lab, when they create colloidals, they will put it in an electron microscope, and that's how they will tell the parts per million. They will not measure it from the amount of material used. While I might have used 5 or 6 or 7 milligrams of material to create ruby red colloidal gold, as far as the video microscope is concerned, we're looking at a 50 parts per million, 40 or 50 parts per million colloidal gold solution. So parts per million does not mean concentration in the solution. The only way to tell your concentration in the solution is by looking at it through a video microscope or an electron microscope, and making a general, count or guess on what you're seeing. So I just wanted you to know all parts per million are not created equal. What they put on the bottle is not the same thing. We really shouldn't measure colloidals by parts per million, but what are we going to do? We have to measure it by something. So, but as you know, I like to show the pictures in the microscope of what my colloidals look like, so you can see for yourself, this is the density of this solution as compared to that solution. And that's all that's really important, because this one or 2 milligrams of platinum, which gives quote a 2 parts per million solution on paper, but a 15 to 20 parts per million solution on the microscope, is very strong as far as how it works in the body. I don't think, cooking this to 10 parts per million using the formula, the general formula, is going to give us something that tastes absolutely horrible and is way too strong. You don't need to cook it that strong. Why waste the platinum, which is extremely expensive? If we can get away with using 1 or 2 parts per million, 1 or 2 milligrams of material on platinum, and getting a 15 to 20 parts per million solution on the microscope, I think we should be very happy about that. So that has changed the way I'm looking at cooking platinum and the results I'm trying to get at platinum at this particular time. I'm no longer looking for a 10 parts per million platinum solution. I'm looking to cook the best 1 to 2 milligrams worth of material, or 2 to 4 parts per million in paper platinum solution that's going to look like a 15 to 20 parts per million solution on the microscope. So that's my goal, and to make it as easy as possible, whether you're going to use low voltage electrolysis or high voltage AC, but the better method, I think, is low voltage electrolysis. I think having the capping agent in there might make it a little bit more stable, because I have no experience with high voltage AC colloidals at all, on how long they actually last before they unravel with no capping agent. Anyway, well, that finishes my long update here. I will talk to you again soon.